Hi there! Did you know that all the elements, even the carbon atoms that you and I are made up of, came from the stars? Continuing on our journey of exploring the life cycle of stars, in this video we learn what will happen to low-mass stars once they have exhausted all the hydrogen in their core. Let's begin. A star on the main sequence maintains a constant energy output by burning hydrogen to helium via nuclear fusion. As we discussed in the previous video, as a main sequence star ages, its luminosity increases slightly, resulting in its expansion and consequent cooling of the outer layers. This explains why the main sequence is a broad band rather than a narrow line. That is because the stars move up and up to the right on this band as they age. Eventually, the hydrogen fuel in the core runs out and fusion stops, shutting off the outward radiation pressure. Inward gravitational attraction causes the helium core to contract, converting gravitational potential energy into thermal energy. Although fusion is no longer taking place in the core, the rise in temperature heats up the shell of hydrogen surrounding the core until it is hot enough to start fusion of hydrogen. This produces more energy than when it was a main sequence star. This shell burning causes some very interesting effects. The new increased radiation pressure actually causes the outer layers of the star to expand to maintain the pressure gradient. As the gas expands, it cools, just as a spray can feel colder after use as the gas has been released. This expansion and cooling causes the effective temperature to drop. Convection transports the energy to the outer layers of the star from the shell burning region. The star's luminosity eventually increases by a factor of 1,000 times or so. During this stage of expansion, the star will move up and to the right on the HR diagram along the red giant branch. A G5 class star such as the Sun may end up as a high K or low M luminosity class 3 giant. The point at which helium begins to fuse in low-mass stars sometimes occurs with the production of a lot of energy almost instantaneously and is therefore called the helium flash. At this point, the star has fully evolved off the main sequence and has turned into a red giant. A red giant displays extreme densities. While the outer envelope extends to as large as 1.5 astronomical units, that is the orbit of Mars, the inner core is dense enough to burn helium into carbon and oxygen via the triple alpha process. Since the density of the outer envelope is lower than the vacuum on Earth, it is barely attached to the core of the star and therefore can be easily ejected. Mass loss from a giant is typically about 10 million solar masses per year in comparison to only about 10 to the power minus 17 solar masses per year from the Sun. The helium core is incredibly dense and only about 1/3 its original size. As a result, electrons within the core are packed tightly together in a volume governed only by the uncertainty principle. In this state, it no longer behaves as an ideal gas, but a degenerate electron gas. Before we move forward, let's try to understand the quantum mechanical concept of degenerate matter, which is extremely important for understanding exotic objects such as white dwarfs and neutron stars. In the year 1925, Wolfgang Pauli demonstrated that two electrons cannot occupy the same quantum state. For instance, if an electron in a ground state hydrogen atom occupies an energy state, the next electron from the electron-proton pair which can be added to it to turn it into helium must occupy a higher energy state. In other words, two electrons cannot hold the same place in an atom at the same time. This is known as the Pauli's exclusion principle. At extremely high densities, such as those prevalent in the helium core of the red giant stars, electrons are forced to occupy higher energy orbitals in order to satisfy the Pauli's exclusion principle, and are therefore referred to as the degenerate electron gas. As the density of particles in a degenerate gas increases, the particles are forced to occupy higher energy states, which further increases the pressure of the gas. This is called the degeneracy pressure. Degenerate matter is very hard to compress because the only way the particles which are locked into place can move is by absorbing energy and moving to higher energy levels. The pressure in a degenerate gas depends upon the speed of its particles rather than the temperature of the gas. The energy released by the helium flash raises the core temperature such that it can again behave like ideal gas, which means it can expand and cool. The energy transferred results in a hotter outer layer of the star but a smaller overall size. The rise in effective temperature and decrease in surface area are such that the luminosity of the star remains roughly constant at about 100 times that of the Sun for almost 100 million years. Such a star tracks across to the left along the horizontal branch on the HR diagram. The horizontal branch stars have helium-burning cores surrounding by a hydrogen-burning shell. Eventually, all the helium in the core of such a giant star will fuse into carbon and oxygen and the core will contract again. Carbon and oxygen nuclei have more protons than helium, so the Coulombic repulsion is greater in them. That is why the temperature needed to fuse them into heavier nuclei must be even greater than 100 million Kelvin, which is required to fuse helium. In stars with mass lower than 8 solar masses, the gravitational energy is insufficient to generate such high temperatures, so no more fusion can take place in the core once helium supplies run off. But the contraction of the core generates sufficient heat for the surrounding layer of helium to start fusing. That is, the helium burning now starts in a shell. Energy from this helium burning shell heats up the surrounding unused hydrogen, which also starts burning in a shell around it as shown here. As the giant star expands again, possibly up to 1.5 astronomical units, that is, equivalent to orbit of Mars around the Sun. It is now an asymptotic giant branch star occupying the upper right portion of the HR diagram. A 1 solar mass AGB star may have a luminosity 10,000 times that of our Sun, making AGB stars some of the brightest and coolest stars in the universe. Outer layers of AGB stars are only weakly held by gravity. The helium-burning shell is not dense enough to be degenerate, so helium flashes occur with a runaway temperature rise. The resulting increased reaction rate generates and releases a large amount of energy. This thermal pulse can last for a couple of 100 years or so. During this phase, nuclei within the helium-burning shell can be synthesized into heavier nuclei through the capture of neutrons and radioactive beta decay. This is called the S process, where S stands for slow, and can produce elements as heavy as bismuth, which has 83 protons in its nucleus. The AGB stars may produce a thermal pulse every 10,000 to 100,000 years. Large convection currents in AGB stars carry materials produced in the thin helium-burning shell up to its surface. These heavier nuclei are detected in the star's spectrum, which thus provide an insight on what is happening deep within the star. The ejected material comprises a mixture of elements including carbon and oxygen rooted up from within the star. The carbon-rich molecules form dust particles that tend to shroud the actual star. As the cloud expands, it cools, but the dust absorbs and re-emits the radiation from the stars at longer wavelengths. AGBs are therefore often more luminous in the infrared than visible wavebands. The expanding cloud can also be observed at radio wavelengths. AGBs such as Mira are intrinsically variable stars with periods of months or a few years. They can vary by up to 10 magnitudes, and their radius differs by a factor of 2 during its oscillations. When the fuel in the helium-burning shell runs low in an AGB star, the outward radiation pressure drops off. As this was earlier holding out the shell of hydrogen gas, this shell now contracts, heats up and ignites, converting hydrogen to helium. This helium ash in turn falls onto the helium shell, heating it up till it is hot enough to reignite in a helium shell flash, producing a thermal pulse. Increased radiation pressure now causes the hydrogen shell to expand and cool, shutting down hydrogen shell burning. The interval between successive thermal pulses decreases as an AGB star ages. For solar mass stars, such pulses dramatically increases the luminosity of the star for several decades. Over time, the outer layers of the AGB stars are almost totally ejected and may initially appear as a circumstellar shell. The ejected cloud contains dust grains of silicates and graphite in addition to hydrogen and elements produced via nucleosynthesis reactions within the parent star. The cloud has typical expansion velocities of tens of kilometers per second. Our Sun will shed about 40% of its mass during this phase. More massive stars lose a greater percentage of their initial mass. With the ejection of the outer layer of the star, its hot, dense core is left exposed. Initially, it is so hot that the intense ultraviolet radiation it emits ionizes the expanding ejected shell. This results in the cloud glowing, similar to an emission nebula. Such objects are called planetary nebulae after their initial description by Herschel in the 18th century. The term planetary nebula is a misnomer though, in the sense that they are not related to planets, even though they appear as faint disks, just like faint planets through small telescopes. Planetary nebulae typically contain 0.1 to 0.2 solar masses at densities which are equivalent to vacuum on Earth. Spectacular images by modern telescopes, including the Hubble Space Telescope, reveal a wide range of shapes that pose interesting problems for theorists to explain. The bipolar nature of many planetary nebulae may be due to the parent star being in a binary system. Strong magnetic fields of remnant cores may also influence the shape of the nebulae. Colors of the nebulae reveal information about their composition. The characteristic blue-green color is from the doubly ionized oxygen lines, that is O3. Oxygen, carbon, and some S-process elements ejected by AGBs are found in planetary nebulae, may eventually seed the interstellar medium for the next generation of star formation. Some of the carbon and oxygen in our bodies may have come from such nebulae. The rest probably came from the supernovae explosions. Planetary nebulae do not exist for long. An expanding shell of dust and gas may only be visible for about 20,000 years or so before it disperses into the interstellar medium. There are over 3,500 planetary nebulae in our galaxies, and many others are visible in other nearby galaxies as well. Planetary nebulae can therefore also be used for measuring distances to these nearby galaxies. Although a planetary nebulae is only short-lived, the exposed core remains. This exposed remnant core that ionized the material in the planetary nebula is basically an extremely hot, dense sphere of carbon and oxygen. Any hydrogen not ejected quickly fuses via shell burning. When initially exposed, the central star with a temperature more than 30,000 Kelvin may have a luminosity 100,000 times that of the Sun. But then, it quickly fades by up to 90% within a century or so. The stellar remnant becomes a white dwarf with a surface temperature of about 10,000 Kelvin. White dwarfs have unusual properties. First of all, they are very small, but the more massive white dwarfs are actually smaller than less massive ones. With their fuel used up, no fusion takes place, so there is no outward radiation pressure to withstand the gravitational collapse. More massive stellar cores experience strong gravitational force, so they actually compress more and are therefore smaller than the less massive white dwarfs. A half a solar mass white dwarf has a radius of about 1.9 times that of Earth, while a 1 solar mass would have only 1.5 times the size of the Earth. A white dwarf is composed of carbon and oxygen ions mixed in with a sea of degenerate electrons. It is the degeneracy pressure provided by the electrons that prevents it from further collapse. A white dwarf with a mass roughly that of the Sun, packed into a volume not much greater than the Earth, must have an extremely high density. At 1 billion kg per meter cube, the density of a white dwarf is 1 million times greater than water on Earth. Although its surface temperature is about 10,000 Kelvin, the core temperature may be as high as 10 million Kelvin. The heat trapped within a white dwarf will gradually be radiated away by it. But because of its small radius, a white dwarf has only a very small surface area. Therefore, heat cannot escape quickly. In fact, it takes tens to hundreds of billions of years for a white dwarf to radiate away its heat and cool down to a black inert clump of carbon and degenerate electrons. As the universe is not yet old enough for this to have happened, all the white dwarfs that have ever formed in single star systems are still white dwarfs. Interestingly, not only are the more massive dwarfs smaller than the less massive ones, they are also less luminous for the same reason as I explained earlier. Typical luminosities of white dwarfs are less than 1 in thousandths that of our Sun. More massive white dwarfs having smaller surface area but more trapped heat take longer to cool down than the lower mass ones. As white dwarfs are so faint, they are also very hard to detect. We are only able to observe relatively closer ones. Nonetheless, white dwarfs are thought to comprise about 10% of stars in our own galaxy. Nearby examples are Sirius B and Procyon B, both of which are found in binary systems. But what is the upper mass limit for a white dwarf? We may imagine that if we increase the mass of a degenerate core, it simply becomes smaller. While this is true to some extent, there is a limit to it. If the mass of the stellar remnant exceeds 1.4 solar masses, then the electron degenerate pressure is insufficient to withstand the force of gravity. The core will then continue to collapse and form either a neutron star or a black hole. The value of a 1.4 solar masses is called the Chandrasekhar limit after the Indian astrophysicist Subramanian Chandrasekhar. He won the 1993 Nobel Prize in Physics for this discovery and now has NASA's X-ray observatory Chandra named in his honor. One point to remember about this Chandrasekhar limit is that it refers to the mass of the material in the remnant core after all the other mass is lost. Stars lose a lot of their mass as they evolve off the main sequence and become an AGB star. The upper mass limit for a main sequence star that will go on to form a white dwarf rather than a neutron star is thought to be about 8 solar masses. A 2 solar mass star will probably end up as a 0.7 solar mass white dwarf. The lowest mass white dwarf known so far has a mass of only 0.17 solar masses with an effective temperature of 11.2 thousand Kelvin. These dwarfs form from main sequence stars less massive than 1 solar mass stars like the Sun. So to summarize, in this video we learned about the post-main sequence evolution of low-mass stars and followed their journey through the red giant branch all the way up to the white dwarf phase. We will continue with the evolution of high-mass stars next week. Do let me know if you're enjoying this series on the evolution of stars and share our content with other astronomy enthusiasts. I'll see you next week. Until then, take care.